In this lecture, we are going to apply ARIMA to the airline passengers dataset. Our main goal in this lecture will be to improve the results we got in the last lecture, which shouldn't be very difficult since we were just guessing. That is, if ARIMA works as it should. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As always, you can check the lectures, how to code by yourself, and how to practice for a more in-depth discussion. If there's anything in this lecture you didn't understand, or you think I missed a step, or didn't explain why we were doing something, please use the Q&A to inquire. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so let's start by downloading the airline passengers dataset once again. Next, let's import pandas, numpy, and matplotlib. Next, we're going to install the pmd ARIMA library. This is necessary because this library does not come pre-installed in Google Colab. Next, we're going to load in our dataset using pd.readcsv. Next, we do a df.head as usual to ensure our data looks as it should. Next, we're going to take the log of the passengers column and store this in the log passengers column. This should be interesting to compare since previously we found that logging the passengers column helped the model achieve better accuracy with the same ARIMA order. Next, we're going to split our data into train and test, with the last 12 data points assigned to be the test set. Next, we're going to import the pmd ARIMA library. Next, we're going to call the ARIMA function. Okay, so what are these arguments? The first argument is the data. That one should be obvious. The second argument is trace. We're going to set this to true so that we can see which models ARIMA tests out while it tries to find the best model. The third argument is suppress warnings, which we are also going to set to true. As you know, stats models has lots of warnings, so this will make sure that those warnings are not printed out. Finally, we set seasonal equal to true since we want to fit a full seasonal ARIMA model, and we set m equal to 12 since we know that the seasonal period is 12. Okay, so let's run this. Alright, so once this is done, we call the function model.summary. So if you've ever worked with R, you should be very comfortable with this kind of output. Alright, so basically this is going to tell you the orders of the best model and other information such as the AIC, the BIC, log likelihood, and the p-values of various statistical tests. You can also see the value of each parameter in the model and whether or not they're statistically significant. Okay, so what's our best model? It looks like our best model is an AR3 for the non-seasonal part, and for the seasonal part, all it does is the first difference. Remember that this is the first seasonal difference, so instead of subtracting from 1 time step behind, it's subtracting from 12 time steps behind. You might actually want to try that in code to see if the result looks stationary. Also note that this is a much more parsimonious model than the non-seasonal ARIMA we found earlier, which was an ARIMA 1210. This model has only 3 weights and 1 intercept. Okay, so next, let's call model.predict. As input, we'll say nperiods equals ntest and return conf_int equal to true so that we can plot the confidence interval. Next, we're going to plot our forecast along with the true values. So first we're going to create an axis object and set the figure size. Next, we're going to call the plot function on the test data frame. We'll give this the label data. Next, we're going to call the plot function on the test predictions. We'll give this the label forecast. Next, we're going to call the function fill between, which will plot the confidence bounds. As with stats models, the confidence bounds are returned as a t/2 array. So each row represents a timestamp, and each column represents either the lower bound or the upper bound. Finally, we call ax.legend to plot the labels. Okay, so let's run this. All right, and we see that our forecast is pretty good. Next, I want to plot a plot of the full model prediction, just like we did before. This will include both the forecast and the in-sample predictions. So first we're going to need to call the function model.predictInSample. We'll pass in start equals 0 and end equals -1 to get the full training predictions. Note that unlike stats models, we do not need to specify that we want the predictions to be accumulated if you have differencing in your model. PMD ARIMA will just assume that automatically. Next, we call all the usual plot functions to make our plot. So let's run this. Okay, so this pretty much looks as expected. Both the training predictions and the forecast look pretty good. One weird part about this graph is the beginning, where all we see is a flat line. Since we now have a seasonal model, it's not possible to make predictions for the first few time steps. This is due to the fact that we require values from one season behind, which don't exist. Okay, so next, since we know that our model might perform better on the log dataset, we're going to run our auto ARIMA again, but on the log passengers. Otherwise, all the arguments to this function are the same as before. So let's run this. Alright, so now let's check model.summary. So as you can see, this finds a slightly different model than the auto-ARIMA on the non-logged dataset. Now we have 2 autoregressive coefficients and 1 seasonal moving average coefficient. Again, we do seasonal differencing rather than non-seasonal differencing. Alright, so again, we have a plot of the forecast against the true values. I'm not going to explain this code since it's exactly the same as the previous code. So qualitatively, the results still look pretty good. Next, let's look at the full train and test predictions. Again, this is the same code as before. Okay, so the plot is kind of hard to see since the first few values stretch all the way down to 0. You could block these if you wanted, but I'm not going to bother. Now, since both of these models look to be performing pretty well, it might be a good idea to test them quantitatively. That is, to use the RMSE. You've seen this function before, so there's no need to explain it again. So let's run this. Alright, so this is kind of the opposite result from what we saw previously. In this case, the non-logged version performs better. Interestingly, we get an RMSE of about 18 something, which is on par with our previous ARIMA 1210 model, the one we found by just guessing. Now, the next thing I would like to do in this script is to test auto ARIMA itself. I want to know, can auto ARIMA find the model that we found last time? So I'm going to call auto ARIMA again on the log passengers. This time, I'm going to set a few more parameters into this function. First, I'm going to set max p equal to 12 and max q equal to 2. If you look at the documentation, these values are set quite low by default. So if we want auto ARIMA to even have a chance of finding the model that we found, we have to set them higher. Note that we also have to set a parameter called max order. This value acts as a limit on the total sum of all the ARIMA orders, which promotes finding a simpler model. Again, the default value is 5, which is very small, so in order to have a chance of finding our previous model, we need to set this higher. I've set it to 14, since that's the sum of 12 and 2. Next, we have an argument called stepwise. This controls whether we use an intelligent algorithm to search the hyperparameter space, or if you use a naive grid search. The default value for this is true, so for now we'll leave it like this and see how it performs. Finally, we set seasonal equal to false, since our goal right now is to compare these results to the results from the previous script. Okay, so let's run this. Okay, so what's interesting about this is that it doesn't even try that many values. In fact, we never get past p equals 5. But perhaps this is a better model than what we found before. If we do a model.summary, we can see that the presumably best model is ARIMA 412. Next, let's plot our model forecast. Okay, so we can see that this forecast is pretty bad. Next, let's plot both the train and test predictions together. Again, not so great. Finally, let's check the RMSE. So as you can see, it's pretty high relative to what we've seen before. Okay, so at this point, what I want to do is to compare what we just did to a full grid search. So let's scroll back up. And let's set stepwise equal to false. And let's run this all again. Okay, so this time, we can see that AutoARIMA is actually testing out all the possible combinations of models. Note that it would not be a good idea to do this if you had a full SARIMA model, that is, both the non-seasonal part and the seasonal part. Again, this goes back to the concept of the curse of dimensionality. Currently, we're only testing out 2 hyperparameters, which is a 2-dimensional grid. If you have, on average, 10 values of each hyperparameter, then that would be 100 values to test. If you had the seasonal part too, then you would have 10 to the power 4 values to test. That's 10,000, which is 100 times more than 100. Okay, so in any case, let's run model.summary. As you can see, the best model appears to be ARIMA 1211. This is very close to our manually found model, which was 1210. Okay, so next, let's plot the forecast. Okay, so that looks pretty good. So already we can see that perhaps AutoARIMA might not necessarily find the best model with the default settings. Next, let's plot the train and test predictions together. Again, this looks pretty good. Finally, let's print out the RMSE. Okay, so we get about 23 something. This is actually quite interesting because this is a worse model than the model we found on our own. As you recall, ARIMA 1210 achieves 18 something RMSE. Furthermore, that model has less parameters than this one, so this model actually gets a higher penalty for having one more parameter. So what this tells us is that finding the best AIC is not the same as minimizing the out-of-sample error. They are similar ideas in concept, but one is looking for a simpler model, purely to look for a simpler model, while the other doesn't actually care about model complexity, but rather accuracy. So these two ideas are related, but they are not the same.